Dmitry Panasenko and his talk based on joint project with Leonid Chalaginov on enumeration of divisible design graphs.
Thank you very much for the introduction. And at first, I would like to thank all the organizers of this wonderful workshop. And now I will remind you some definitions that you already heard today, but it will be useful in the next minutes. Okay, so disagraphs were introduced in 1999 as a generalization of strong irregular graphs, and the definition of disagraph is a k-regular graph on the vertices if the number of common neighbors of any two distinct vertices takes only two different values, A or B, and we say that B more or equal than A. And we say that the disagraph have parameters V, K, B, A. Disagraph is called strictly disagraph if it has diameter 2 and is not strongly regular. In 1999, the complete list of strictly disagraphs with at most 13 vertices was presented in the same paper as the disagraphs were presented. And in 2011, an algorithm for enumeration of disagraphs was presented by Sergei Goryainov and Leonid Shalaginov, and this list was extended up to 16 vertices. And in 2019, this algorithm was improved by Sergei Goryainov, Leonid Shalaginov, and me, and this list was extended up to 21 vertices, and all adjacency matrices are available at this link. And if you're interested in studying disagraphs, you can visit this web page and look at this graph in more details. And let me remind the definition of divisible design graph. A k-regular graph on the vertices is called a divisible design graph, or DDG in short, with parameters vk, lambda1, lambda2, mn, if its vertex set can be partitioned into m classes of size n, such that two distinct vertices from the same class has exactly lambda1 common neighbors, and two vertices from different classes has exactly lambda2 common neighbors. Note that DDGs with m equal 1, n equal 1, or lambda1 equal lambda2 is a VK lambda graph, and in this case, we will call such graphs improper divisible design graphs. Otherwise, we call them proper. And the definition of divisible design graph implies that such graphs are disagraphs. And one little definition before we talk about enumeration. A graph is called walk regular whenever for every L more or equal to the number of closed walks of length L at a vertex set X is independent of the choice of X. Examples of walk regular graphs are strong regular graphs and vertex transitive graphs, but that they are not bounded by only strong regular or vertex transitive graphs. Divisible design graphs were first studied in master thesis by Maike and Meilenberg, and in this work, the list of feasible parameters of divisible design graphs up to 50 vertices was presented. In two following papers, the one Vladislav Vladimirovich Kabanov talked some minutes ago by Hemers, Kargani, and Meilenberg, and another one by Hemers and Sinkovich, feasible parameters of divisible design graphs up to 27 vertices was studied in more details, and the existence of graphs with such parameters were resolved in all but one cases. We'll talk about that a bit later. And divisible design graphs has at most 5 distinct eigenvalues, and you can see the formulas for their multiplicities and the formula for eigenvalues itself on the slide, at this table. And let's talk about searching for physical parameters. So we fix the number of vertices, and when we'll consider all possible number of classes M and class sizes N. After that, the parameter K runs through from 3 to V minus 3, and both lambda1 and lambda2 run from a maximum of 0 or to K minus V to K minus 1, the extension of cases for which lambda1 equals lambda2, lambda1 equals 0, lambda2 equals 0, lambda2 equals 2K minus V. For these cases, all possible divisible design graphs are known and can be obtained from strong regular graphs, and constructions were listed in paper by Himmers, Haragani, and Meilenberg. The next step is for remaining possibilities. We check whether K squared minus lambda 2V and or K minus lambda 1 are squares. If they're not, the corresponding multiplicities are equal. So F1 and F2 or G1 and G2 in some cases. And at the last step, we can reject some set of parameters. In the cases for lambda 1 equals K minus 1 and odd N is excluded. The case then K squared minus lambda 2V equals K minus lambda 1 is excluded. The case then both multiplicities for both sets of eigenvalues are equal is excluded. The case then multiplicities are not integers is excluded. And if the only one of K squared minus lambda 2V or K minus lambda 1 is not a square, the yet undetermined multiplicities can be computed. The case when they are not integers is also excluded. The next step is to consider a quotient matrix. So let me remind the definition. Let V1 union V2 union and so on Vt be the partition of the vertex set of a graph gamma with the property that every vertex of Vi has exactly Rij neighbors in Vj. Then this disjoint union will be an equitable T partition of graph gamma. Matrix R, which contains all numbers of neighbors for our classes in partition, is called the quotient matrix of equitable partition. So for example, let us consider divisible design graph with parameters 8, 4, 0, 2, 4, 2. You can see it here. And all parts of a partition colored in a different color. So we have 4 parts of size 2. And the quotient matrix of each partitions will be all one matrix, for example. In case of divisible design graphs, the partition into M classes induce equitable M partition. And for the quotient matrix R of this partition, we have the following properties. So for example, diagonal elements can run through 0 to n minus 1 because we cannot have loops in our graphs. Other elements can run through 0 to n. The sum of each row equals k, and there is a matrix equation for R squared. You can see on the slide below. These properties will give us some nice restrictions for enumeration of quotient matrices. For given parameters vk, lambda 1, lambda 2, mn, we calculate all feasible parameters. We generate all possible R11, and for all obtained R11, we generate all unordered partitions of k minus R11 as sum of m minus 1 numbers. We use unordered partitions since the permutation of R1j for j more or equal to does not change the final result. For example, these two rows, 1, 5, 5, 7, and 1, 7, 5, 5s gives us the same quotient matrix up to class renumbered. We can change class 4 with class 2 and so they are equal, and we can consider only one option. We check if generated row satisfies the equality for R squared. If not, we reject this row. We repeat steps from 1 to 3 for other rows, so second row, third row, and so on. But we generate ordered partitions this time because we cannot be 100% sure if we have the same matrices up to class numbering or not. And after we generate all possible I rows of the quotient matrix, we leave only non-equal up to classes numbering option. So here is the table of all feasible parameters for proper DDGs up to 27 vertices, which was given in paper. More about divisible design graphs, and the case which marked red was not resolved. In this paper, the authors used quotient matrices to prove the non-existence of some DDGs with given parameters, considering various properties of matrices. They proved the impossibility of their existence, and so the non-existence of divisible design graphs. Our approach allows us to automate this process. For example, this exact case for 27, 16, 12, 9, 9, 3 remained undecided. Our algorithm produced 0 possible quotient matrices for these parameters, so there are no divisible design graphs with these parameters, and the question is resolved. At the time of this talk, we have already found all possible quotient matrices up to 39 vertices. And the last step of our three-part algorithm is the enumeration of divisible design graph itself. For given quotient matrix, we generate all possible rows of adjacency matrix, relying on no partition into classes. We say the two partially filled matrices are equivalent if the graphs determined by them are isomorphic with respect to partition into classes. After addition of a new row of the adjacency matrix, or partial matrices were checked for equivalence, and only non-equivalent were considered for adding the next row, and so on. We generate all possible divisible design graphs. So the next two slides contain the table of all proper divisible design graphs, with exclusion I talked earlier, up to 27 vertices. So we have 3 non-walk regular graphs here, and 5 non-walk regular graph here, and also for 24 vertices we have 6 non-isomorphic divisible design graphs with given parameters and given spectra, and so on. And I talk about the case marked red in the next slides. In paper by Himmers-Kargani and Malenberg was given the following necessary condition for the existence of divisible design graphs. If there exists a divisible design graph with parameters vk, lambda 1, lambda 2, mn, then each of the following Diophantine equations, you can see those equations on the screen, has an integral solution x, y, z other than 3 zeros. In this, let us consider case 27.84293 as possible parameters for divisible design graphs. In this paper, they were also given a table of feasible parameters up to 27 vertices, and these parameters were rejected as not satisfying the necessary condition of the previous slide. So let us consider 2 Diophantine equations. So it's exactly these 2 equations with given parameters. We have 4x squared minus 3 to the power 9 y squared equals z squared. And we have integral solution 5, 0, 10. And 10x squared plus 6y squared equals z squared with integral solution 1, 1, 4, for example. Thus, these parameters are satisfying the necessary condition. So there could be divisible design graph with such parameters. And as our enumeration shows, there is one not walk regular divisible design graph with these parameters marked red at our table. Actually, there are more enumeration results. So let me show you next table. So we have computed almost all cases up to 34 vertices, with the exception of 6. These cases are hard to compute because in all of them, k equals to v over 2 and lambdas equal to k over 2. And it takes way more time than all other cases, but we're definitely sure what it will be computed quite soon, maybe by the end of this week, who knows. So yeah, and actually for the parameter set 28, 15, 6, 8, 7, 4, there are 60 isomorphic divisible design graphs, 17, 4, 52, 10, 6, 2, 4, 8, and so on. So some parameters gives us one case, some parameters gives us a lot more. And as a conclusive remark, when we finish our enumeration, all found adjacency matrices and some properties of divisible design graphs found with us will be available at the same web page as adjacency matrices of these graphs. So I hope this update will be released very, very soon. And thanks for your attention.
Thank you, Dmitry, for a very nice talk with new results. Are there any questions to Dmitry? Well, I have a question. Yeah, good talk. Yeah, so that is from William Hammers. Yeah, good talk. Very nice talk. Yeah, I do agree. And actually, I wonder. So you said that you enumerated all quotient matrices up to 39 vertices, right? Yeah.
Yes.
Does this mean that you plan to enumerate all DDG up to this number of vertices?
Yes, we plan, but if it will take a really long time, we probably stop. But consider other cases. Maybe in the resulting table at the web page will be as analogy to site with list of strong irregular graphs marked with yellow. So we don't know how much DDG with these parameters, but we know that there are quotient matrices satisfying that, because enumerating quotient matrices is faster than enumerating divisible design graphs.
Well, but you said long. What does it mean long? Long, how long?
Months, maybe.
So what,
if we don't have results in a week, maybe we abandon this case for a while and can switch to another.
Well, but your plans are to get up to which number of vertices?
Well, ideally 63.
I see.
Ideally, but we have doubts that we can go up to this number.
I have a question.
Yeah, sure,
yes.
please.
Dima, do you know which graphs, which divisible design graphs from your list are Kelly graphs?
Not already, but I can be checked very easily because we have a database of Kelly graphs and just check isomorphism.
Yeah.
I think it will be useful.
Yeah,
and this information, of course, will be available at the web page at the time when it will be.
Good, very nice. I hope that for the next workshop, which will be on November this year, I hope you will give us complete information, which will be obtained up to November.
We hope to. We hope so. We hope so.
Okay. Are there any other questions to Dmitry? If not, then let us thank Dmitry again for this very nice talk. And actually, we started with divisible design graphs and Cayley graphs, and now we have one more talk, I mean this talk by Dmitry on enumeration of divisible design graphs. So that is very nice to have at least two talks dealing with this class of graphs. And Vladislav told us that actually this class of graphs is one of the complicated to classify desert graphs. So it is very important to know this information. Thank you very much, Dmitry. So good luck in your further investigations.